Okay. We're on the ratio there. Now, if the P portion right here, and you can see that where people have the proportional and the integral used by themselves or the proportional by itself, if it's used by itself, the control will never reach set point if the load doesn't change, okay? All right, follow me through on this. Let's say we have a constant load, and the load never changes. And as we get closer and closer to set point, the valve, the cooling valve, let's say we're cooling, it's a cooling application, we'll get to that point where the valve is fully closed before it actually ever reaches set point. So that droop that we talked about earlier, the difference between the set point and the difference between the control point will be that droop right there. Will stay there. You'll never capture it. You'll never capture it. So if that's proportional is the only one used, then you'll always have a droop. It can be weighted in the PID. In other words, it can be used twice in the summation, or it can be used 3 times, or it can be used once. It can have a weighting, and you typically, when you're setting the PID up, that's when you do the weighting. And it's one of the algebraic functions that are summed as part of the PID. Integral portion. Basically what it does is it offsets the set point. So let's say we have it set for 72 degrees and it's way away from that set point. So what we do is we set the set point to something higher to make it work harder, okay? So it basically offsets the set point so that the desired set point can be achieved. And that's what it does. It'll offset it inside the machine, but you'll still have to set for 72 up there. But inside the PID, it'll be telling it, oh, it's really 71.5 or it's really 73 according to what you really need. And it can be weighted. It can be weighted as a part of the PID, just like the others can. So it can use it 1 time or twice or 3 times, and it's part of that algebraic function as well. The D is to minimize the oscillations, okay? And it looks at the slope of the curve. So if we have a function of an algebraic curve that is proportional directly, it'll go up like this. Well, it looks at the slope of the curve and it sees what the curve's doing. And it takes a look at that slope, and if the slope's getting further away from where it's supposed to be, it takes action. It basically drives the valve open more. But the main function of the D portion of it is to prevent the oscillations in curves. It kind of like predicts the future. It's kind of looking in the future tense of it. And again, it can be weighted as a weighted part of the PID, so it can have more authority than the others or less. And it's also a part of that summation of the algebraic function. PIDs, remember we said it a minute ago, they work on errors. You're either on target or you're away from target. That's all it knows. On or away. And it looks at the error. And the P portion looks at the present error, the error right now. The I portion looks at past errors or a history of errors. As a matter of fact, if you're tuning a PID, you'll look at it and it'll have accumulated errors. And it'll have a field over here on your software screen, and it'll show you what those accumulated errors are. And then the D predicts what the future error is going to be, so it can have the authority that it needs to make the control go where it needs to go to. P is a ratio, I is an offset, and D is a forecast. That's really kind of what you need to remember on this whole thing that I've been talking about. So if you forget everything that I've been talking about for the last 7 minutes, and you remember right there, that right there, you'll be doing pretty good as it comes to PID. P is ratio, I is offset, and D is forecast. Now I know right about now you're probably saying, unless you know this already, dadgummit, I don't think I'm ever going to get this. Well, we all sit in that position one day. You guys are 20 and 30 something, I'm 60 something. So there's a big difference. You will get it. It'll come to you, and like I said, that 10th time around the track, you know, finally, eureka, it'll hit you, and you'll get it. So don't give up on these things. We're going to talk about now sequenced outputs, what they're used for. They're used to drive this valve right here, which is a stepper motor. And basically that means it sequentially moves. It sequentially moves. And I'm going to be real quiet right here for a second. Can y'all hear that valve moving? Can I hear that? Okay. That's moving 200 steps per second, okay? If you watch those lights right there, that's moving 1 step. And you're going to see how that correlates to the position of that valve. Now, do you guys use step valves in automobiles? And do you work on cars?
That's actually like oil changes and stuff.
Okay, well, y'all probably have stepper valves in the damper operators for the air conditioning things. You know, those are probably stepper valves in sequence there. But you see how that sequence is open and closed? It's closed right now. Can you see those lights? Okay. Now that's sequence now. And I'm going to leave this here so y'all can play with it later. Basically, they sequence the valves. They operate off 12 volts. And they're basically, you have two types of valves. You have a unipolar and a bipolar. Bipolar is of course, has two. Uni means they're all connected together. The sequence is, each one of those increments right there is a step. If you could actually look in that valve, and if you go to, I tell you, there's a good application. If you Google stepper motor, Wikipedia, is that what I'm saying? Am I saying it right? Wikipedia. And if you go on the Wikipedia, there is a picture that looks something very similar to this, and it shows that animation of that stepper motor working. It's one of the best animations I've ever seen, and it shows the sequence of the lighting, or how they're energized and how they move the valve around. Okay, but they're very, very accurate. Very accurate. It's one good thing about stepper motors. This shows the motor sequence, the sequence of lights that were flashed a minute ago, and the open and the closed sequence, and just basically shows how they step the valve around for those sequences. Basically, the valve movement operates by a motor turning, which turns a threaded stud that comes out of there, and then this pin moves up and down on that thread. Sporlan has a name for that. Digital interaction. You see, you got the stepper motor right here, and it looks like a clock mechanism. The threaded action right there, and then there's a pin on the end of that to control the refrigerator. Now, have you guys taken a regular expansion valve apart yet? No. Y'all need to do that. It's basically a little pin and a carrier, and it's kind of like that, except it moves up and down based upon the movement of this valve right here. Just a higher pitch resolution picture right there. The EXV is the unipolar valve, which is the least expensive valve. It's kind of made, this would be what you see on a residential application right here. This valve right here is the SCR valve, and this is what you would see like on a commercial application or a refrigeration unit, i.e. a closed door case. You know, 5-door frozen food case is where you would see this. But you would actually see it would be down in the bottom of the case, I hope. Drop that thing right there. Yep. Typically, the valve would be in the bottom of the case where the coil is, and this device right here would be on top of the case, up on top of the case up there. And there'd be an interconnecting cable just right here between the two of them. These are larger valves. This probably you would see on a chiller. This is something that you would see on a cascade system, refrigeration system that may have CO2 on the top cycle. It's a larger valve. And of course this right here is all Sporlan's valves and their applications that they have right here. And I think they go up to 400 nominal tons, if I remember correctly, R22. Some of the things that you need to know when you're functioning here, and I'm only saying this so that when you pull that sheet open and you begin to play with this valve a little bit, you'll know some of the parameters that you have to program or the steps. Some of them they all have different steps, like this ESX valve. It's kind of a cheap valve. It's 400 steps between fully open and fully closed. The valve right here that we have, this SCR valve, is 2,500 steps between fully open and fully closed. So this valve, if it's the same tonnage valve, this valve is going to have more resolution in it. It's going to give you tighter control. And it's a lot more expensive valve than that ESX valve is right there. Some of the other valves are higher tonnage valves, the SCI 50 and 175. But anyway, the important part of this is if you have this specific valve and you're configuring or setting up the parameters in this controller, you have to match the steps up with the step function in here, okay? You'll see that when you do it. Okay, the controllers look like this. Now, basically you walk up to this, and the reason that actually I had the idea of building this and I asked David to help me with this. I told him what I wanted to do. We have cases that have electronic valves in them, refrigeration cases like you guys do. And I wanted something where my guys could come to the office, because typically I get a call say, "Hey boss," or "Big Cheese" is what they call me sometimes. I'm getting ready to go to the deer camp and I want to hurry up and get out of here in a hurry. And I got this valve that looks like this, and I get this white box up here, and I don't know how to make it work, which is this thing right here, okay? And it's got Kelvin 2 on it. And I say, "Well, Cookie, don't you know how to make that thing work?" He said, "Well, if I did, I wouldn't be calling you." He says, "And we got about 15 minutes because I'm leaving to go to the deer stand here in just a few minutes, you know." So I got this thing that David and I built so that a guy could come up, like y'all, plug into it with his Cat 5 cable and see exactly what he's going to see in the supermarket. Okay? And this particular application would be a supermarket application. The heat pump that I told you about in my house, it has this, had that EXV, that black looking valve on there. Its control is part of the heat pump control board, okay? It doesn't have a separate control board like this. Now see, is that a powered uniform? Y'all sell Linux equipment, right?
We do.
And y'all have variable speed, y'all have these stepper valves in some of your product,
That's
right? Do y'all have your an independent controller for them, or does Linux have their own board controller that controls?
Linux has their own.
Okay, good. Do you know what brand that y'all use particularly? Are they Alco or Danfoss or Sporlan, or do you know?
I'm not quite sure actually.
Okay, it's hard to tell from looking at the valve unless you know exactly what you're looking at. And sometimes, you know, they have look-alike valves, or sometimes there'll be an OEM valve, and then, you know, so you won't be able to tell. But it's still relevant, because when you have their valve, you default to their material, and they'll tell you exactly what you need to know. But it's good to know this because you'll have some kind of idea of how the valves work. But anyway, so we did this so a guy could walk up to it, plug into it, and typically you'll have one of these for every 3, 4, 5 door case according to what you have. Every expansion valve will have one. Here is the valve right here, but it's actually mounted right in here on this unit cooler evaporator right here, okay? It's mounted right here. But in the case, it would normally be down in the case. So, the good thing about that is used to, remember we want to check the superheat on something, we would have to go open up the case and pull the product out of the bottom of it, pull the pan up and get down in there and start checking superheat. Now all we have to do to check the superheat is we plug this device in right there at the on top of the case right there, device, and we can see what our superheat is. We can see what all the parameters are on this thing, and right now it's in the position of right there 0, and the temperature out, or the temperature coming out of the tail of the coil, is 70 degrees, and the state that it's in is in superheat is, hold on, 55, and let me get over here to the state. The state should be in pump down mode, okay? Because I put this little switch up here to emulate a pump down. In other words, a relay says pump it down, okay? So it's in the pump down mode. So right now it's not calling at all. All right. You can get them with the display on them, but when you got 100 of them in the store, it's a lot cheaper for the manufacturer to put that on there and then have one display unit to go around the store. Now they can be interlinked together on what they call a mod bus, or network together, and you'd have a laptop. You go to the laptop, you go to the address, or you could even use this on this address bus right here. Still use this device right here and go to the address that you want, and then hit the button, jig the button as J. Clower says, and then get the parameters off of that valve. Yes, sir.
Now, can you run all those without the display and hook them up to where you can control them off of a E2?
I don't know if you can control this particular valve off of an E2. I know that you could control an Alco valve off of an E2. But now, let me go back and say this. I think that the E2 controller does have a Modbus function in here. And the E2 controller has Modbus, and this also speaks Modbus. Now, Modbus is a control language, okay? It's really kind of a primitive control language, but it's a common control language that everybody's controller speaks. So, yes, you can speak through the E2 to this through Modbus, but you may have to jump to a different level, you know what I mean, to get to that level, versus just walking up and linking into it. Yes, sir.
Now, how is that wired into the system?
Okay, how is this wired into the
controller.
system? Okay, this right here?
Uh-huh.
Okay, now this is just a Cat5 cable, like you'd use to connect any kind of Ethernet together with, or a bus together with. It's just a Cat5 cable. I plugged it in here, and I plugged it in here. Now this is, and this is one of those things that y'all can look at later, and y'all could even, if you want to, wire it and unwire it. This is wired into this system right here. Can you see that good right there? Mm-hmm. Okay, so you have those cables that go up. You have a cable that goes, of course, you power it up through the transformer, through those terminals right there. You have a cable that goes up to the expansion valve. You have a cable that goes up to the pressure transducer, which is right here, okay? And then you have some input switches. Right here's an input switch for pump down. I'm just faking it out with this pump down switch. You have a thermistor right here that comes over and wires into it. And then there's a suction line thermistor over here that wires into it. Now, it really only uses two of those devices for control of superheat, and that's the suction line temperature and the pressure transducer, the two things it uses to calculate superheat, okay? So that's what it does. And so that's how it's connected to the system. Now remember, this would be connected to the in close proximity. And I say that because I think this cable, you can get it in, they call it meters, but if you string it out, you can see it's pretty long. It'll get you a 12-foot case. You can put the controller up here and then loop your cable down and get to the valve at the end of the case if you want to, okay? So that's how long that is. So that would be up on top of the refrigerated case, and then of course that would be down in it. Now your other pieces would connect by those cables, by way of those cables there, okay? Did I answer your question on that?
Yes.
This is, I'm going to leave this with you too so y'all can play with it. This is a diagram that shows those connection ports. In terminals 13, 14, and 15 is the connection port for that Modbus, okay? So if you wanted to communicate with other controllers, then that's where you would connect it to, is to that Modbus. Now, but on this application, we just have one controller. But you could gang them together, so to speak, and have multiple controllers on that, okay? I have two different kinds of sensors, and remember I'm going over this because these are what we're using now. We're talking about the sensors that we're using now. This sensor that we passed around with the brass was a 2 or 3K sensor.
3K.
Thank you, 3K sensor. Notice it kind of looks like it's maybe going a pipe or mount onto a pipe there, and it is. And when you connect it, you want to make sure that you've got some type of thermal contact grease right there. And guys, this is a spoiling picture. I don't know why they put those wire ties on. That's the first no-no of mounting expansion valve bulb or sensors. You don't use a wire tie because you're not going to get good thermal contact with that. You don't want to over clamp it either, but you got to use metal. David, you had a statistic
I think
earlier today.
If I recall, one of the seminars that we was in, I think the presenter said that 2/3 of the transfer is done through the actual hardware, meaning the mounting material, to the thermal buck. Now, I got to looking at that one. That bulb is actually, or that sensor is actually contoured to fit on a pipe, whereas a regular the regular power head sensor would not be. It's like putting two zeros together. If you look at two zeros, you really don't have a whole lot of contact where the two are. This may be a little bit different, Steve.
Yeah, you know, it might be, David. I ain't gonna, you brought that up this morning, and I am gonna ask them. Now, you know, they do make a tie that you clamp down with a gun. Y'all seen that, where you like pull it and it pulls it really tight. But I am gonna ask Sporland what their preferred method of connecting these things to the suction arm. I know we've been doing this for years. We use a metal clamp. We use a metal clamp for how we clamp them there. But I'm going to ask them if this is acceptable right here or not, or it may just be for demonstration purposes only. I don't know. David, how do we do ours on here?
I don't know. I'm afraid to look.
I think we got it covered up. Guys, whatever y'all do, y'all can do anything, but do not take this piece of insulation off back here. It might be ugly into there. I don't know.
Steve, if I may, things like that, I had no idea about that until I went to a seminar. Now, I can't say that traveling from here to LA would have been cost effective there to learn that little bit, but I learned much more out there. But you'd never quit learning unless you're as old as Steve.
I don't quit learning. I'm being serious when I say this. I learn something it doesn't matter who I talk to that's in the business, and I don't care how long they've not been associated with the business, I'll say how green they are to it. I always learn something from listening to them. When you go to a seminar or something, I've learned stuff from guys who've been in the business less than a year, and I've been in it since 1971. And I'm still learning stuff from guys that are younger. They have a new perspective, on the way they look at things. So it is important, as David says. And did you learn that in LA, David?
I think I did.
That was good. Tell them what else you learned, David, in LA.
Beautiful out there.
I'm going to ask your class this question. Can I ask them?
You go right ahead.
Okay.
I deserve this.
This is a question I want to ask y'all. A heating device called a convector transfers heat primarily by A, osmosis, B, stratification, or C, convection. What would your answer be? Would you say that? Well, our dispatcher, who don't know nothing about air conditioning or refrigeration, was in the room, said the same thing. But Taylor, what was your answer?
Pass.
We were jet lagged. We really were. We were jet lagged, weren't we, David?
Yeah.
We were tired. And plus, they didn't say it. They had a bunch of guys talking. They don't talk like we do from up in Pittsburgh, and then they had some from California. They just don't speak like we do down here. We were in the back. For some reason, they put us in the back of the room this time. Did you notice that, David?
Yeah, I did. But
we won the first ever trophy, didn't we?
Yeah, we did. I just went completely blank, and if that's my excuse, and I'm sticking to it.
It wouldn't have been sociable to go out there and kick their butt in California and bring the trophy back, David. Just go ahead and say it.
I wanted the trophy back. I'm not going to be nice about that.
Can I get back to the lesson plan here?
Yeah, please.
Okay. Mount it traditionally like you do a regular expansion valve bulb in the 4 or 8 o'clock position. When you're making electrical connections, guys, these are your connections right here. Use these 3M Scotch locks, UR2s, or whatever UR that you have that you're using, because they do a couple things. They make the connection, and they provide a sealant in here. Probably the #1 problem with these things is after they've been installed, I guarantee you open up the bottom of the case, you see a couple of wire nuts in there with tape on it. They get corroded, and it changes the resistance of this, so it doesn't read right. So you got to use these connectors right here. They cost a little more, but you got to do it. Pressure transducer, it is very specific. The thermistors and transducers are very specific. this is not one of them right there, but the one that's on there, has a plug that matches it and is used for its purposes. Basically, when you see this right here, when you get the material and you start looking at it, playing with it out in the lab, you'll see that we have the 150 transducer in there, and you can calculate your voltage and see what the pressure is to make sure it's accurate. That's basically for calibration purposes. Is you take your voltage minus 0.5 volts, multiply by 37.5 on this particular transducer to give you what the pressure should be. Okay. Now, I don't know if I said it just right. If I put that pressure gauge on the low side of the system, and I measure the voltage between pins 34 and 35, I believe. You can double check me on that. And the voltage should be, take my voltage minus 0.5 voltage times 37.5. That's what my voltage should read on my VOM. Okay? That's DC volts, by the way. DC volts. And they'll tell you whether it's accurate or not. And then there's an offset in here, and it tells you how to do that, to do the offset, to calibrate this and the thermistors as well. There's a quick connection diagram of it. The connections that we were talking about, how's it wired into the system. Basically, you bring your 24 volts in here. This right here is a 240 volt 3 amp rated contact. It is not the voltage coming in. Yours truly almost wired it up that way right there, but my buddy back in the room, the little short fat guy with a bald head, said, "Steve, you don't want to do that." It was kind of late in the afternoon. I said, "What do you mean, David?" "Oh, I'm sorry, I didn't mean to call you." He says, "That's a switch right there." I said, "You know what, David, you're right, that's a switch right there." So, but anyway, you be careful of that. That is a relay contact right there. These are the connection points for the transducers, the various sensors, the pump down switch, the communication port. I don't have that hooked up right there, okay? This is a little closer connection to it. In your appendix, the handouts that I'm going to leave with you, you'll see that the processes that we talked about right here, when we look at this controller, that come up, or right here, dial on it first, then tells you how to get down into the controller, to drill down into it. The passcode is 111, and then when you get down and drill into it, you have the processes without just plugging in, and you have those basic processes right there. But if you want to drill down and start changing stuff, the passcode is 111. It's written on there, so you don't have to remember that. But then you have all these other parameters that you can change and set, okay? And don't worry about getting it out of discombobulation. I want you to open the valve up, let the machine run, watch it flood back, try to bring the superheat down to 2 degrees, set the superheat high, do whatever you want with it, okay? Remember, if you tear it up, we can fix it. We can fix it. Don't worry about that. Have some fun with it, and observe the refrigeration system as well. There are a couple of site ports on here, so you can see this should be vapor and oil coming back. You'll see liquid coming back, coming out of the accumulator. You'll see liquid coming out of there too, if it's flooding back bad enough. So observe those things. Use it as a kind of a trainer as well to observe the refrigeration system. This device right here slows the fan up and down, or cuts it completely off. It slows it down to reduce the load. You can watch it, suction pressure change, or you can add the load to it by speeding it up. The rocket scientists can figure that out, didn't it? Just so you'll know, you've got the switches here, one's for the compressor, one's for the whole machine, the other one will cut the compressor off if you want to do that. And this is the pump down switch up here, and which means the pump, it's in pump down mode right now when it says on. That's not going to be in these instructions right here. But anyway, you can get to all these other parameters that you want to set and change. And it tells you what the defaults are and whether they're changed. And when you begin to do this, okay, if you forget everything else I've talked to you about tonight, about the droop and the PID and all that, if that's just not like clicking with you yet, when you start to mess with this thing is when you'll start getting it, okay? When you start seeing the superheat coming down, when you start seeing the suction line frost up, when you start seeing those things change in the coil, actually take your thermocouple and measure these different parts of the coil. It's a single circuit coil, and see how these temperature changes affect it at different loads. And just do some labs. When you start doing this, you'll start getting a connection with the device and how it works, okay? So do that. These are some alarms that come out, and basically this is on your sheet 2. It tells you what alarm you get and what's going to happen when it gets that alarm. And the first 2 right there, it goes into a pump down mode. If you have a sensor failure or a transducer failure for your pressure, it goes into the pump down mode to protect the compressor. If you have a low superheat mode, it goes into a super hyperactive mode where it really starts to close the valve quickly so as to get the superheat up. Because remember, we want superheat to protect the compressor, right? That's what we want to do. Is that them or me?
That's them.
Okay. And then high superheat, it just gives you an alarm out with no response. Okay, resources. www.storelingonline. And you got these 2 bulletins right here. They are also in that sheet that you'll have. It's great. So, questions. You got questions you want to ask me? No questions? Okay, good. When you get that thing in the lab, don't do that. Do everything but that. I've done that several times. Several times. I will end with one short story. One short story I'll end with. And actually, David and I built this device right here. We actually took it up to Murfreesboro, Tennessee, and did an RSCS presentation with it on this and some other stuff. But back, y'all know who Muhammad Ali is, don't you? The boxer. Mm-hmm. How about Ernie Shavers? Y'all remember him? Ernie Shavers was kind of a big guy, bigger, not as big as Larry Holmes, but almost as big, but bald-headed, just a brutal kind of boxer, you know. He was just a brutal guy. And so Muhammad Ali was mine and David's favorite fighter, and he was boxing Ernie Shavers. It was going to be better than the Thrill of Manila, and it was on TV. And so I had one of them big TVs that weighed about 400 pounds at my house. This was when we were in our 20s, wasn't it, David? Early 20s.
Early 20s.
My wife had taken the kids, and she'd gone up to her mama's house, and me and David had the house to ourselves, and we were sitting there watching the TV with our little snacks, and the TV looked good, and the fight was getting ready to come on. David says, I just was at the Votech school, and I took a TV repair course, and I could make it TV brighter. I said, yeah. He said, yes, I even have this special plastic screwdriver to adjust it with.
Yep.
I said, okay, David. As he gets back in, he tweaks on a little bit. I said, oh, David, that looks good. He looks up, you know, he's all him. We weren't as fat back then. We were both skinny. And he gets up on there, he looks at, I can do better than that. He him a little bit. That's good, David, that's good. He looks up a little bit. He said, I can do better than that. He twists a little more, and all of a sudden you hear something, and it looks like a cartoon. There's a big puff of smoke and all this electrical stuff coming out of the TV, and the TV goes blank. We didn't get to see. I didn't get to see.
No, you didn't get to
go home.
I went home and watched it.
I was gonna kill him.
No, that I knew Beverly was coming home.
Yeah, Beverly was coming home. So, but anyway, this is 40 years later.
Yeah.
40 years later, me and him are in Murfreesboro, and my wife sends me a text and says, tell David not to be working on any TV sets while he's up there. So, what goes around comes around, doesn't it?
Probably don't want
So, don't let the smoke out of it, of yourself. You can let the smoke out of that, but don't let the smoke out of yourself. Okay, guys? All right. Well, y'all been a great class. I thank you for putting up with me, okay?
Thank you.
All right. I'm going to leave this